Hello everyone, I am Siddharth and now I am going to give a presentation on the topic linear feedback systems as a part of the PHN 313 coursework. Well, to begin with, let us ask ourselves a question: what exactly is a feedback system? Feedback system is one that uses the system's current output to cause variation in the applied input signal in order to obtain the desired output. Simply said, the presence of a feedback system enables for a continual comparison of the system's reference input to obtain the intended output. These systems are typically utilized to provide a more corrective response by comparing the produced output to the applied input. Let me describe this in context of the inverted pendulum example. Let's say that we have a mechanical system which consists of a cart, and the cart can move in one dimension, uh, as is shown in the figure, and it has mounted on it a rod with a weight on the top, and it pivots around the base. So that represents the inverted pendulum. There is an acceleration that can be applied to the cart, and that will be thought of as the external input. And then on the pendulum is the force of gravity, as is marked on the diagram, and the set of external disturbances that might represent air currents with or whatsoever that will attempt to destabilize our system, that is, make the pendulum fall down. If we look at it in a straightforward way, we have the system dynamics and several inputs, one of which is the external disturbance, and the other input is the external acceleration that is applied. The output can be thought of as the angular displacement that we want to be balanced, that is, make it zero. Now, if we know what exactly the system dynamics are and if we knew what exactly the external disturbance is, we could design an acceleration which is an input that would generate zero output. That is zero angular displacement. But this is not the case, sadly. So what we would be doing is measuring the output angle and then using the measurement to somehow influence the applied acceleration. This now becomes an example of a feedback system. If we choose the feedback dynamics correctly, we can drive the output to zero. So by applying feedback, what we are trying to do is we are trying to stabilize this inherently unstable system. Now, an inherently unstable system is the one which is itself unstable if left free on its own. Another example corresponds to the problem of positioning a telescope, which is mounted on a rotating platform. Uh, the rotating platform is driven by a motor. Again, we could imagine the possibility of driving this to the desired angle by choosing certain applied input voltage. But that is again only possible if we know about the external disturbances, as in the previous case. So we are again motivated to employ a feedback, which is to make a measurement of the output angle and use that in a feedback loop to influence the drive for the motor. So so that the telescope platform is positioned at the desired angle. Basically, this is what we are trying to achieve. The measured output and angle would be fed back and compared with the desired angle, and the difference between these two would be put through a gain or attenuation as and used as excitation to the motor. Now, if we abstract away from the telescope positioning system, we here have a more continuous time system. We here have a more continuous time system sound, which we want to apply, some feedback, which we could do it with a continuous time system or with a discrete time system by first converting these signals to discrete time signals, then processing that with the discrete time system, and then through the appropriate interpolation algorithm, we could convert that back to a continuous time signal, and the difference between this feedback signal and the input signal forms the excitation to the system that we are trying to control. We can move the continuous to discrete time converter up, and we can move the interpolating system outside the summer. We end up with what looks like a discrete time feedback system in the diagram on the right. Basically, what I'm trying to emphasize is the fact that feedback arises not just in the context of continuous time systems, but also the analysis of discrete time feedback systems becomes important. Let us discuss one example of a discrete time feedback system. Population studies are examples of discrete time feedback systems. Let's say that we have some type of model for population growth. And since people come in, of course, people come in integer amounts, obviously, that output represents the sequence. That is, it is indexed on an integer. And typically, such models are unstable systems because the population keeps on growing exponentially. Now, where does the feedback come in? It comes in when we incorporate in the overall model various retarding factors. For example, as the population increases, the food supply decreases, and that is a feedback process that acts to retard the population growth. Of course, there are there can be other retarding factors apart from the decreasing food supply. Now, we are going to look at some basic properties of feedback systems. To do that, let's look at the basic block diagram and equations for feedback systems. Beginning with the continuous time case on the left, we have a system h of s in the forward path and a system g of s in the feedback path. The input to h of s is the difference between the input to overall system and the output of feedback loop. The output of the adder is called the error signal. To analyze this system, to analyze this feedback system, what we would do is we would begin with writing some equation, and it is best done in by writing the system function and best done in the frequency or Laplace transform domain rather than the time domain. As I have labeled through freehand writing on the diagram at the left, y of s is the Laplace transform of the output, and that of output from g of s is y of s into g of s. At the adder, the input is x of s, and the Laplace transform of error signal is x of s minus y of s times g of s. And the Laplace transform of output of the system output of the system h of s is the input multiplied by h of s, which is equal to y of s. So solving for y of s over x of s, which of course is the overall, which is nothing but the overall system function, we get the expression as written below in the diagram after a little bit of rearrangement. Exactly the same kind of procedure would work in the discrete time. Now we are going to look at some common applications to highlight the importance of feedback. Everything will fall out in a straightforward way up from these feedback equations, just as derived in the previous slide. So the first example is that of a feedback in the amplifier design. Suppose we have built an amplifier which has a good amount of gain, but has the problem that its frequency response is not actually constant. If we embed the amplifier in a feedback loop, where in the feedback path we put an attenuator, then we can compensate for the non-constant frequency response. Let us see how this works out from the feedback equation. We want to look at the frequency response, so we look at the Fourier transform, and the frequency response of the overall system is the frequency response of the Fourier transform of the output divided by the input, that of the input. And using the feedback equation, we can write the second equation as well. If k times h of j omega is chosen to be very large, then the overall system function varies approximately as 1 over k. Basically the implication is that we have flattened the frequency response, but the price that we have now paid is the gain is reduced now. Now another example is in implementing inverse systems. Suppose that we have a given system P of s, and what we would like to do is to implement the inverse of the system, which has a Laplace transform or system function as 1 over P of s. By putting this in a feedback loop, we can implement the inverse of the system. Can we do this? The answer is yes. The feedback system is indicated in the diagram as shown. We put the system P of s in the feedback loop, and now using the equations we derived in the earlier slides, the system function is k over 1 of k over 1 plus k times P of s. Now if we choose the gain k such that it is much greater than 1, then the system function varies approximately as 1 over ps. In this case, the inverse of the system with system function P of s is approximated by the feedback system. Now, finally, to examine the stability, we know that we examine the roots of the equation 1 plus g of s times h of s equal to 0, which is the denominator. Now, as long as we choose g of s uh, such that the poles of this equation are on the left half of the s plane, uh, we know that the system is stable. But this applies only for the continuous time case. Now the basic difference between continuous time and discrete time cases in terms of stability is the fact that the stability condition in discrete time is different than that it is in continuous time. In the former, we care for poles of the overall system being whether they are, and talk about whether they are on the left hand side or the right hand side of the S plane. But in the discrete time case, what we do is we check whether the poles are outside or inside the unit circle. So in the discrete time cases, we would impose for the system to have uh, zeros such that they have magnitude less than 1. Now, finally, before concluding, I would like to add another point that there's the other side of the coin as well. If we start with a stable system and put a feedback around it, what can happen is in fact we can destabilize the system if we are not careful enough. One very common example is in audio systems when we have the speaker and the microphone in close proximity. Well, this is all from my side for this presentation. Thank you for listening.